In our previous lectures, we talked about how to obtain the state equation in order to formulate a given circuit. Okay. In this lecture, we will discuss about obtaining the solution for a given LTI state equation, x that equals Ax plus Bw. And we start with this simple case where we don't have any inputs. Okay, so x that equals Ax only. So that means the solution will depend only on the initial condition of our dynamic components. And such equation, such state equation without any input term is called the homogeneous state equation. Okay. Now, suppose we have obtained somehow, or perhaps given, the state equation for some LTI circuit. X that equals Ax, where X contains our capacitor voltages and inductor currents within our circuit. With X is in Rn, suppose that we're talking about a circuit of order n. Okay, so therefore X, our state vector, is in Rn, it's of size n. And that makes this A matrix, which is always a square matrix, of size n by n. Okay. A is an n by n real matrix. Furthermore, in order to obtain the solution, we need the initial conditions, and that's also available. Suppose, okay, x0 equals x0. Since this is an LTI system without loss of generality, we can take the initial time to be 0. Okay, so clearly this too is a vector in Rn, that is initial capacitor that contains initial capacitor voltages and initial inductor currents in our circuit. Now the question is, supposing that we have the model, we have the formulation of the circuit, and we have all the initial conditions available, how to obtain the solution for future time, t greater than or equal to 0. How to compute x of t. Okay, so we'll talk about this question. So we're going to start with a guess. We're going to assume that somehow there exists a matrix of size n by n, and that matrix has functions as its entries. Okay, so its entries are time variable. So there exists a matrix which we're labeling m of t. And for each value of time, it's a real matrix in Rn by n. We're going to call it, for now, a matrix function. And suppose that that function, that matrix, satisfies the following two properties, or two conditions. Condition 1. When you plug in t equals 0, okay, its value is the identity matrix. So m0 equals, this is identity matrix in n by n dimensional space. Okay, identity matrix. So that's condition 1, which we assume our imaginary matrix satisfies and hypothetical matrix satisfies. And the second condition is that when you take its time derivative, and taking the time derivative of a matrix simply means you take the time derivative of every single entry, and it has n squared entries. Okay. Its time derivative, which again is a matrix of same size n by n, equals at any time t a times the matrix itself. times mt. Then we can somehow find such a matrix that simultaneously satisfies these two conditions. It turns out that by using that matrix, we can easily obtain x of t, the solution. How? It's as follows. Then x of t equals this matrix times the constant vector of initial conditions. x0 would be a solution. Okay, would be a solution means that that function x of t will simultaneously satisfy the differential equation constraint and initial condition constraint. Now, since we're talking about an LTI differential equation, an LTI system, if you have a solution, that it is the solution, okay? Because the solution is always unique. Therefore, that x of t, which we will now show satisfy simultaneously both of these constraints, would be the solution of our problem, okay? Would be the solution, because the solution is unique, because all we have to do is whether it satisfies these two conditions. Let's start with the initial condition constraint, because it's easier to check. X of t evaluated at the initial time, which is 0 for our case, must equal x of 0. So let's see whether this candidate satisfies that. Equals n of 0 times x0. By assumption, n of 0 is identity matrix. So what we have therefore is I times x0, and identity matrix times any vector equals the vector itself. Okay, therefore it satisfies the initial condition constraint. Initial condition constraint satisfied. The other thing that it should satisfy, if it is the solution, is clearly the differential equation. So let's see whether it satisfies the differential equation or not. So let's compute x dot for this candidate. d over dt xt equals d over dt, and then we put in our candidate this matrix times this constant vector. Since the vector is constant, we can take it outside differentiation and write d over dt mt times x0. And what's this derivative? Again, by assumption, that derivative is a times, okay, it's this a, the matrix itself, mt. Okay, so therefore we have a times mt, it's this derivative, times x0. But this product here, m of t times x0, is our x of t. Therefore, this we can write as a times x of t. Therefore, what we have is x dot equals a times x, meaning that the differential equation constraint is also satisfied. Therefore, this matrix, if it exists, is a magical thing, because using it we can obtain a solution in a straightforward way. Now, therefore, our question is, can we find or can we construct a matrix M of t which simultaneously satisfies those two conditions? And the answer turns out to be yes. Okay, now let's talk about how to obtain that M of t. Now, here's a guess on M of t, which would result in satisfying those two conditions. And our guess is this, M of t. Suppose that we construct this matrix by adding infinitely many terms in a summation. And the first entry of our terms is the identity matrix of size n by n. Okay? And the next term is t times A. A is our system matrix, the matrix that appears in our state equation. Then the next term is t squared over 2 times a squared. The next term is t cubed over 6 times a cube, and we now see what the pattern is. We go on forever. Okay, now since we're summing infinitely many terms, the convergence is an issue, and it turns out that we're not going to go into details. It turns out that for all A matrices and for all T's, okay, this sum with infinitely many terms will always converge. That means for all A and T, this is a well-defined function. Okay. Now, with this construction, it's very easy to check that it satisfies the two conditions, C1 and C2. The first is, in fact, obvious. Plug in t equals 0, and all these terms disappear, and you're left with identity matrix. And its derivative equals A times M of t is also not difficult to check. Therefore, this construction, this matrix, satisfies both C1 and C2. Then M of t satisfies C1 and condition 2. Now this matrix, M of t, is called, not surprisingly, because this is the series expansion of an exponential function, scalar exponential function. Now we're, in a sense, generalizing it to matrix value functions. M of t, therefore, is called a matrix exponential. Okay. Or sometimes state transition matrix. Okay, it has many names because it's an important matrix. And usually, not surprisingly, denoted by e to the at. Okay. E being our 2.7128 and so on. But in this case, when we write e to the at, it means, by definition, a square matrix. Okay, square matrix function. So let's therefore write M of t. Now we're calling it e to the at, using our series definition. Okay, summation k equals 0 to infinity tk over k factorial times a to the k. Okay. In this expression, again, we use the convention that any matrix raised to the power 0 is, by definition, identity matrix. And then this object is our state transition matrix. And then, once you have the state transition matrix, solution to the homogeneous state equation equals Ax with initial condition x0 equals initial condition vector x0 is x of t equals e to the at state transition matrix times x0. Okay. So we have obtained sort of the solution to x dot equals Ax, homogeneous state equation. Now let's talk about or list some properties, okay, of the state transition matrix. All will follow from the definition. Some are easy to show, some are not that easy to show. I'm not gonna go into details, but it's always good to know these properties which may become handy for analysis. Properties of state transition matrix. Well, some properties of the state transition matrix. There are many properties. First, e to the a t1 plus t2. A is a matrix, t1, t2, they are scalars. Okay. This equals, it turns out, for all real scalars, t1 and t2, e to the a t1, okay, times e to the a t2. Okay, so that's our first property for all t1, t2 real scalars. Second property, which is easy to show, is that e to the at evaluated at t equals 0 is identity matrix, which directly follows from the definition for the series construction. 3 e to the at, okay, is a matrix n by n. It turns out that this matrix for all t and for all a, okay, is invertible. So in general, an arbitrary square matrix doesn't have to be invertible, okay, but this matrix for all a and t is always non-singular. And its inverse equals e to the minus at. That is, you evaluate e to the a, let's call tau, at tau equals minus t, and then the matrix that you obtain is the inverse of e to the at. All t in R. Okay. So let's put a remark here about non-singularity of e to the at. E to the at is always invertible. Okay. It is non-singular or full rank, however you may want to call it, for all matrices A and for all times T. And the fourth property that we want to list is the following. Again, it follows from the definition very easily that A times e to the at, A is an n by n matrix, e to the at is also an n by n matrix. Okay. So the result is again an n by n matrix. So if you take two arbitrary square matrices of the same size, let's call them n1 and n2, n1 times n2 does not, in general, equal to n2 times n1. Okay. So in matrix multiplication, you don't have commutative property in general. But if those two matrices are A and E to the AT, then for all A and for all T, those two matrices will commute, meaning that this equals E to the AT times A. Okay. So the matrix exponential always commutes with its, let's say, generator A for all T and A. Okay. Now here we have a definition, and we can use in principle this definition to construct this state transition matrix, which is very important, which has key importance in obtaining the solution of a linear time invariant system. Okay? But it would be difficult and probably not feasible, at least for large order systems, to do this infinite summation. Okay, so we have to check for simpler ways, and there are many simpler ways. And one of those that we want to mention is computation by Laplace transform. So let's do that. Obtaining e to the at for a given A matrix by Laplace transform. Okay, note that. Remember that Laplace transform is a very, very useful tool for solving LPI differential equations. Now we're going to use it exactly for that purpose. X dot equals AX. So this is our vectorial differential equation in time domain. So let's transfer this equation to Laplace domain, by which we mean taking the Laplace transforms of both sides of the equation. Okay. So what we have is Laplace transform of x dot, and here we have a Laplace transform of a times x of t. A is a constant matrix, x is a function. Okay, it's a vector x of t. Now Laplace transform of x dot, or any function, that is s times the Laplace transform of that function. Let's stick to the convention and use the capital letters to indicate the Laplace transform of time domain signals, minus lowercase x at t equals 0. So s times Laplace transform minus initial condition. So that's the Laplace transform of the left-hand side. For the right-hand side, we have Laplace transform of AX. A is a constant matrix, therefore we can carry it outside transformation and write A times Laplace transform of X. Okay. Then let's carry or collect the X terms at one side. So what we have is S times X of S minus A times X of S, and then we carry the initial condition to the other side, X0. Okay. Then write something times X of S equals X0. A common mistake is writing this something as S minus A, but this subtraction is not allowed. Why? S is a complex valued scalar, whereas this is a matrix. You cannot subtract the matrix from a scalar. So you should never forget this identity matrix here. Okay, so we have Si minus A times X of S equals this vector. Therefore, X of S, the Laplace transform of R, X of T, must be this matrix inverse multiplying this vector of initial conditions, x0. And then let's go to time domain by taking inverse Laplace transforms of both sides. So what we have is inverse Laplace transform of x of s, which is x of t, and that equals inverse Laplace transform of Si minus A inverse times the constant vector x0. Okay. Now, since this is a constant vector, we can take it outside inverse Laplace transformation, and we can write inverse Laplace transform of Si minus A inverse. So this will be something, a function of time times x0. Okay. Now, x of t equals something, and this something is function of time, and it's a matrix because you're taking the inverse Laplace transform of a matrix times the initial condition vector. Now that we have the same structure, x of t equals a function, matrix function times the initial condition vector. Therefore, whatever this function is, since the solution is unique, this function must equal e to the at. Therefore, e to the at, we have obtained a way to compute e to the at using inverse Laplace transform. So once again, we started from the state equation, homogeneous x equals Ax. We take the Laplace transform and then we collect x of s at one side and all the rest the other side. Then we take inverse Laplace transform and obtain x of t equals something times x of 0. And we know that x of t equals e to the at times x of 0. And we also know that the solution is unique. Therefore, that something here, okay, must be the state transition matrix. So let's put our finding in a box because it's important. E to the at must equal inverse Laplace transform of Si minus A inverse. Okay, so that's one way to compute E to the at without performing that infinite summation. Okay, let's apply our finding on a simple example. Simple but instructive enough. Okay, let's consider lossless LC circuit. Okay, for simplicity, let's take both L and C values, inductance and capacitance, to be 1. So here we have a capacitor connected in parallel or in series, whatever, depending on how we want to look at it, with an inductor. Okay. Capacitance is 1 farad and inductance is 1 Henry. This is our capacitor voltage, VC. Let's also take it to be the inductor voltage. And this is our inductor current. Okay. Now, let's obtain the solution for this system. Note that we can solve this circuit by our circuit theory 1 knowledge, because it's a lossless second order parallel or series RLC circuit where R is absent. So, C dVc, where C is 1, equals what? Equals IC. What's IC? IC is minus IL. Okay. What else? Let's write the Roman equation for the inductor. L dIL, in this case just dIL because L is 1, equals VL. And VL is no other than VC. Therefore, to differentiate this once again, you have d squared Vc equals minus dIL, and minus dIL is minus Vc, so what you have is d squared Vc equals minus Vc. And then collecting all the Vc terms at one side, what you obtain is, okay, d squared plus 1 Vc equals 0. Right hand side is 0 because we have no input in this system. So it will be just, the solution will just depend on the initial conditions, namely initial capacitor voltage and initial inductor current. Okay. For the general case where C is arbitrary and L is arbitrary, we would have obtained d squared plus 1 over LC times Vc. And square root of 1 over LC is what we call the natural frequency of the circuit. Okay. Now, by looking at this second order differential equation, we immediately see that characteristic polynomial is d of s equals s squared plus 1, and the roots of the characteristic polynomial, by definition, we call the natural frequency of the circuit. So the natural frequency So RS12 at plus minus J. They are purely imaginary. Okay, now, since we know the natural frequencies, we have a guess, well, we know the structure and form of the homogeneous solution, and by applying the initial condition constraint, we can obtain the solution for this lossless circuit. So let's go ahead and do that. So what we know, therefore, is Vc of t will be a sinusoidal function, where the sinusoidal value oscillations are at 1 radians per second. And that any such function can be written as a summation of cosine and sine. Okay. And K1 and K2 clearly depend on the initial conditions, Vc0 and IL0. So let's figure them out, because it's quite easy. K1 is no other than Vc0. Plug in t equals 0. This sine term disappears, and you have K1 equals Vc0. And how about K2? Differentiate this once. What we have is minus K1 sine t plus K2 cosine t. Plug in t equals 0, and then this term will disappear, and what we have is K2. Therefore, K2 is rate of change of capacitor voltage at the initial time. And what's dVc? dVc is minus IL, therefore K2 equals minus IL0. Hence, we know K1 and K2 in terms of the initial conditions at this point. So let's rewrite VCT. VCT equals Vc initial times cosine t minus IL initial times sine t volts. Okay. Having figured out VCT, let's also quickly write down ILT, because all we have to do is differentiate it and put a minus sign in front. So ILT equals minus d VCT, and that equals what? Vc0 sine t plus IL0 cosine t. Okay. So let's write it here. So that's what ILT is. Now let's forget about this guy. So what we have obtained is, we have obtained both the capacitor voltage and inductor current for our lossless LC circuit. Okay, so let's call this set of equations star. Now what we're going to do is, we're going to obtain this equation by our new method, x of t equals e to the at times x0, and see that whether they match to one another, which they should. So that's what we're going to do. Let's obtain the solution Vc and IL, which we're calling star. Let's obtain star by using our new discovery, namely state transition matrix. For that, we need the state equation, x that equals ax. It's already on the board. All we have to do is put it in the formal representation. Okay. So let our state be capacitor voltage and inductor current. Then x that equals a times x. We don't have an input, therefore we don't have plus Bw term. So this is a 2 by 2 matrix, because the size of the state is 2. This is a second order system. Let's figure out the entries of that matrix. Entries are already on the board, as we said. First state variable is Vc. Therefore, for the first row, we look at Vc dot. What's Vc dot? Vc dot is minus IL. In other words, Vc dot equals 0 times Vc plus minus 1 times IL. 0 times Vc plus minus 1 times IL. How about the second row? Second state equation is IL. So for the second row, we have to look at IL dot equation. And IL dot is here. Namely, IL dot equals 1 times Vc plus 0 times IL. 1 times Vc plus 0 times IL. And this is your A matrix. Okay. And now, let's try to obtain the solution by, using state transition matrix, and let's obtain state transition matrix using inverse Laplace transformation. And hopefully, in the end, we will obtain what we have obtained using our EE201 techniques. Okay, so what we have to do is we have to compute the inverse Laplace transform of this matrix. So even earlier than that, we have to obtain this inverse. Okay. So let's write down Si minus A first. That's Si is S0, 0S, and then from that we're subtracting A. Therefore, Si minus A is 1 minus 1S. Therefore, Si minus A inverse equals 1 over the determinant, which is S squared minus 1. So that makes S squared plus 1. And then times the matrix, which we obtain by swapping the diagonal terms, SS, and negating the anti-diagonal terms, minus 1 and 1. And here we have our inverse of Si minus A. And then we're going to take the inverse Laplace transform of that matrix, and taking the inverse Laplace transform of a matrix simply means taking individually every entry, inverse Laplace transform of every entry. Hence, inverse Laplace transform of equals inverse Laplace transform of the first entry, which is this times that S over S squared plus 1. And then inverse Laplace transform of this times that minus 1 over S squared plus 1. And so on. Inverse Laplace transform of 1 over S squared plus 1, and finally inverse Laplace transform of S over S squared plus 1. Okay. Now, we remember from our Laplace transformation tables that this is cosine t, this is minus sine t, this is sine t, and this is also cosine t. Therefore, we have all the entries, and that means we have our state transition matrix. So, this, therefore, equals L inverse Si minus A inverse equals Laplace transform of this is cosine t. Laplace transform of this is minus sine t, and so on. Cosine t. Okay. And then what remains is we have to multiply initial condition with the matrix that we obtained, state transition matrix. So let's do that. This is our e to the a t. Hence, x of t must equal e to the a t times the initial condition vector x0. That equals what? So what was our state? Our state was VC and IL. Okay, so VCT and ILT must equal, therefore, cosine t minus sine t, cosine t times initial state, by which we mean initial capacitor voltage and initial inductor current. Then, if you perform this multiplication, for the first entry you have cosine t times VC0 minus IL0 times sine t. And for ILT you have VC0 sine t plus IL0 cosine t. Note that this is no other than what we have obtained and called equation star. Okay, now let's, for the remaining time, let's briefly talk about the more general case, namely non-homogeneous state equations solution. To the general case or the non-homogeneous case, x that equals ax plus b times w. Okay. Now we will obtain the solution x of t again using Laplace transform. So we start from the state equation. This time we also have input. And this equation, which is in time domain, we transform it to complex frequency domain or Laplace domain. What we have is S minus initial condition vector x0. That's Laplace transform of x dot, and then we have a times xs plus b times w of s. A and b are constant matrices with constant case. And then, as before, let's collect the x term, x of s term. On one side, we have Si minus A x of s equals x0. This is what we had for the x that equals ax, but now we also have the w term. So that means we have plus b capital W of s. Okay, and then multiply both sides with the inverse of this matrix, which gives us x of s equals Si minus A inverse initial condition plus Si minus A inverse B times W of S. And then we now take the inverse Laplace transform. Okay, inverse Laplace transform. This becomes x of t, our solution. Now the solution depends not only on the initial condition but also on the input vector. The inverse Laplace transform of this is, we already know, it's e to the at times x0. Okay. E to the at times x0. And then, how about the inverse Laplace transform of that guy? Now what we have is, we can consider this guy as a function of s, and this guy another function of s. So what we're having is multiplication of two functions of s, okay, in Laplace domain. And then if you convert that to time domain, that multiplication manifests itself as convolutional integral. And what we have is from 0 to t, e to the a, t minus tau, b lowercase w tau, e tau. Okay, and from this step to this step, what we have here is convolution integral. Okay. Therefore, we have obtained the solution to the general case. Let's write that down once again. Okay. Therefore, general solution to non-homogeneous LTI state equation is x of t equals e to the at times the initial condition vector plus the term which represents the effect of the input, and that term contains an integral e to the at minus tau b times w of tau d tau. Okay, so let's call this equation 1. Now we have two pieces, as we see, and those two pieces have, not surprisingly, the following names. This is called the zero input solution. That is, when you kill all the sources, this term disappears, and what you have is the part of the response due only to initial conditions. And if you do the reverse thing, that is, set all the initial conditions to 0 and figure out the response, what you obtain is you obtain part of the response due to the input or inputs. So this is called, therefore, the zero state solution. That's our answer to the very first question, that is, what's the solution to the state equation. Now, of course, in order for this to be the solution, it should satisfy two constraints, and we're not going to show them, but instead it's left as an exercise to be shown. So show that the general solution 1 satisfies what it should satisfy, namely the initial condition constraint and the differential equation constraint. X dot equals a times xt plus b times w of t. This is almost immediate, and this requires just a little bit of work, but it's also doable. Okay, now before we end, let's talk a very nice application of what we have just obtained. An application that's valid for circuits with a single input. So that's our last example for this lecture. Given the system which represents some circuit, let's say x equals ax plus bw, and suppose that that circuit is such that it has a single input, a single independent voltage source, let's say, or a single independent current source with scalar input W. Find the impulse response. Usually when we talk about an impulse response in 201, we have in mind, okay, some output of the circuit, some capacitor voltage, some inductor current or something else, some current or voltage. But now we're sort of generalizing that notion, and we're trying to figure out impulse response for the entire state. Okay? So what is meant by this example is you have a single input system. Again, by definition of impulse response, you set all the initial conditions to 0 and apply from the input a unit impulse function, and the question is, what's the resulting x of t, what's the resulting state? Okay, for state. And we have everything we need on the board, which is this general solution for the state equation. So here goes the solution. What we have is x that equals Ax plus Bw, and now W is not an arbitrary input, but it's unit impulse times delta t. Okay. Now, since W is scalar, E must be an n by 1 matrix, so in other words, it must be a vector. Okay, and by definition, the initial condition set to 0. All the capacitor voltages and inductor currents are set to 0. So, let's write down the solution, x of t. It's already here, so what we have is e to the at times initial condition, but initial condition 0, therefore this term will disappear. 0 input solution is gone. Plus from 0 minus to t e to the a t minus tau b delta tau b tau. Okay. So this is gone because all the initial conditions are set to 0. And then, well, when we proceed, note that we have e to the a t minus tau. Remember, one of the properties of the state transition matrix, this can be written as e to the a t times e to the a minus tau. And since the differentiation is with respect to tau, we can take that e to the a t term outside integration. Okay, so let's do that. E to the a t, and then we're integrating from 0 minus t e to the minus a tau b times delta tau. And then what's going on is we have the impulse function multiplying a continuous function. Okay? And then therefore that means we can use the shifting property of the impulse function and write this once again as e to the at from 0 minus to t e to the minus a tau times b evaluated at time, at point, which makes the argument of the impulse 0, which is tau equals 0 times the impulse. Now, we can use another property of the state transition matrix. Plug in tau equals 0, so what you have is e to the a times 0. And e to the a times 0 for any a is identity matrix, and then what we have is identity matrix times b, which is b itself. Therefore, we're talking about a constant matrix, constant vector. That means we can take it outside integration. Okay. Shifting property. And then when you take outside integration, that b, what remains is you're integrating the impulse function, and the result is 1. Therefore, okay, so this thing here is b. Therefore, the overall answer is e to the at times b. Okay, that's a very interesting result. So for a scalar input system, if you apply impulse from the input, set all the initial conditions to 0, what you're going to obtain is the same as what you would have obtained if you forget the input and set all the initial conditions to the entries of the B matrix. Okay. Therefore, this is the impulse response for the state x of t equals e to the at times